We are live.
Yeah. Hello everyone. Welcome to the MLRW's fourth day, and I am Ayush. And today we have Amanpreet Singh with us. Amanpreet Singh is a research engineer at Meta AI Research, working in language and vision team. He is also the author of widely used Glue dataset. Without any further delay, I will hand over the stage to Amanpreet to start the talk.
Hi everyone, I'm Amanpreet and thanks Ayush for the intro and thank you for hosting this talk and inviting me. So I'm a researcher at Meta AI Research and I've been working there for 4 years. And as you can see on the right, there is a link for the slides if you want to follow with the slides or use the QR code to access the slides. So today, the topic of the talk today is towards unified models, a foundation model for vision and language alignment. So let's start with a brief intro for me. So I started with my career at IITR. I was an undergrad student there, and then I moved to NYU where I did my master's, specifically in artificial intelligence. And I worked on Superglue, Glue, and Cola there. And then I moved on to join Meta AI Research 4 years back, and since then I have been working on various kind of vision and language problems, and specifically there, we also built a framework called MMF, which is used widely externally in the OSS and also internally in Facebook for multimodal problems. So let's first talk about what exactly is the topic of today's talk. So in short summary, we are going to talk about how do we build models that can solve tasks across domains. By domains, I mean here different kind of domains that are prevalent in deep learning, such as NLP, natural language processing, and then computer vision, and then also multimodal domains where we are doing some sort of reasoning over vision or language together, or even video or something like that. So they are also domain specific tasks such as ImageNet for computer vision classification, then Glue benchmark for NLP, which have come with their own variety of challenges. So let's see what are the key challenges here. So why do we care about this problem? How do we build the models that can solve tasks across domains? So there is a natural shift towards having a single model solving most of the problems that you can see. As a human, we can also process language, we can process speech, we can also process images. But as of now, the machine learning architectures are very domain specific. For example, CNNs had been very heavy architecture that was used in computer vision uh, applications, and they couldn't one-to-one map to the text side of the things, even though there were some works that did that, but they were still very well suited for CNN for computer vision tasks. And then RNN and LSTMs were too common for NLP tasks, but they wouldn't work for something on the computer vision side. like uh, that said, there are ways you can make them work, but they're still too domain specific for those particular problems. So as a step towards artificial general intelligence, it makes sense to have a model which can work across domains and can solve all kind of tasks that you can think of, whether it's ImageNet classification or doing some visual question answering where given an image you have to answer a question, or even some sort of question answering from a paragraph, or an open-ended question answering. So we would want to have a single model which can do all these kind of tasks, so that we can also save on compute and as well as on other kind of research. Okay, uh, so what is the other key challenge in making this work? So the multimodal data is not abundantly available. If you think about it, stuff like text or images by itself alone are very easily available. But when you think about things where images are captioned, image and text pairs, they are not abundantly available on the internet. So there are ways where they are weakly aligned but not properly aligned, for example taking all text from the images on the net and then using it. But most significantly, even if you see them, they are not properly aligned. So they are data sets that provide image caption pairs for these kind of training, like if you want to do some sort of multimodal pre-training or like multimodal training, then they are data set, but they are all small in nature. So that's one of the key challenge that we will be facing when we are moving towards like a single architecture for solving all these kind of things. Then other than that, like there is like a whole challenge in like making them work. Like jointly learning across domains in itself is very hard, because multitasking across domains requires very careful control and experimentations. Like let's say like you are working making the model to work for NLP, and then you like start introducing computer vision into the picture. You have to like control the parameters properly so that you don't over fine tune for NLP or over fine tune for CV. Then even if you do that, there is like some sort of catastrophic forgetting that always happen when you start from unimodal domains, let's say BERT, and then you try to do multimodal domains. It either gets too fine-tuned for multimodal domains and then starts forgetting like simple stuff like paragraph compression or like question answering from paragraphs. So this catastrophic forgetting happens because like as you as you move towards multimodal domains, you get accustomed or fine-tuned more towards that particular task rather than like being a generic model. So like in this figure, like this is from one of the papers that we will talk about, and one of my prior recent work. So like if you want like the model to do all these kind of tasks such as object detection, VQ, visual question answering, then visual entailment, you will have to like come with some sort of easy way of not doing catastrophic forgetting or forgetting like the original unimodal task while learning multimodal tasks, and also like figuring out how to do multimodal training across all of these particular tasks. Then these like problems require like massive compute. So this is one of the key challenge that anyway you will face, because as you're moving towards like more generic models, they will become bigger and bigger because they require more capacity to learn more stuff. So like in these kind of cases, you can easily require like 2000 GPUs just to like have like a minor sweep run over these models. So these models are getting bigger and bigger with massive batch sizes that are required for them. And at any point, like if you have any questions, feel free to interrupt me. So these are the key challenges that we will face when we are moving towards a generic architectures. So before we go more deeper into this, I think it will be good to like take a recap of transformer and attention, so that we have a good idea of like how the further models that we will talk about are working. So let's first talk about like attention. The attention allows, so attention is a mechanism in deep learning that has become quite prevalent in most of the tasks that we will talk about, and even all of the domain that we're talking about, whether it's speech, whether it's computer vision, whether it's NLP, like attention is the mechanism that you will see in the deep learning everywhere. So what exactly is attention? So attention allows you to focus on specific parts of a given scenario in simple words. Like let's say if a scenario is represented in as a bunch of tensors, let's say like image patches, if an image is divided into like some patches of squares, then these are some bunch of tensors that you're getting. So attention helps you like focus on these on specific parts of these tensor which are relevant to the given context. So this is like a very wordy definition of what attention is. Basically, like if you see this example as a first example on the top, we are trying to like generate a caption for the given image. At each time step where we are generating the caption, you will have to focus at different aspects of the image. For example, at the second time step, bird, you have to focus on the complete bird and ignore rest of the surroundings. And then like similarly, as you go towards water, it's focusing on the rest of the surroundings except the bird itself. And then the body, there's like always a nuance, no, some nuance in like how the attention works. Similarly, for the rest of the examples, like you can also reverse engineer it. Like if given a frisbee, we can see where exactly model is looking at in the image to figure out where the frisbee is. So this attention can help you figure out where exactly the model is looking at, because instead of focusing at the picture as a whole, you are focusing at some specific part of the image now. There are other examples as well for stop sign, and then trees, and then people, and then the girl sitting on the bed. So attention helps you focus at a specific part of the image. So Let's see like how does this work in like the case of text. For text, like you can have some sort of like self attention between the words of the sentence, where like at a particular sentence, let's say it, if you want like a representation of it, you will get like a combination of rest of the words which can correspond to it. For like example, in this case, it's focusing mostly on the animal because that's the representation of it after attention. So attention has to focus on like specific parts of a particular input, and this is very useful in most of the cases that we see today in the deep learning. So let's talk about like how exactly attention can be applied in practice. So attention can be applied on vectors as a probability distribution. Let's say you have like X vector, you can like set a probability distribution for these X vector among like which one is how much important, and then you can like get like a combined sum of them. So yeah, you can calculate this distribution based on some condition that is given to you. Like in for example, in this case, like we were generating a caption, so the condition is like bird. We want to focus on the bird. So you want to like get the tensor representation based on the bird, which is the condition given condition. So the weighted sum that you get based on this condition is used in the further layers as an input and represents the current important context from the previous input. So basically, like if you generated bird for the previous image or for the previous time step, it will pass on that we have generated the bird, which is the combination of the tensor vectors from the image, to the next layer inside the neural network. And then the next layer, we know this was what was generated at the previous time step, and then it will accordingly generate the further time steps inside the text. So this can also be used like we saw in the task involving sequence. Each time step can have its own context weights. So let's see how it's actually implemented, um, like what we discussed in the probability distributions. Let's see how it actually can be implemented in like actual code or like actual mathematical definition. So the like this is where like the transformers paper, which is like attention is all you need, comes into the picture. It provides like a theoretical framework for defining attention easily, and then also stacking these attention layers on top of each other so that you can have like multiple layers of attention instead of just one, and do a better job at addressing your task rather than just like having one layer or two layer. You can have like 12 layers of attention transformers. So in a simple words, like attention mappings in transformers network can be described as a function of a query and set of like key value pairs. So the values are what we like take softmax upon, and query is what we care about, and then key is also helps in like calculating the soft attention weights. So transformer use a scale dot attention mechanism to obtain a context vector. So for example, you take transpose of the key and multiply it with query, and then divide it by the square root of key dimension, and then take a softmax on top of it, which gives you probability distributions for each of the values, and then you multiply them with the values to get a single context vector. So this is what happens inside like the basic building block of a transformer. So you also like mask out the invalid connections to the future in case of like sequences, because you don't want to see the future. So you mask them out to preserve the autoregressive property of the network. And then you can also like apply multiple of these scale dot products to create multi-head attention. So like we as a human, we don't just focus on one place at a single time. We can focus on multiple places at a single time. When I'm looking at a image, I can like focus on a different aspect. So to replicate the same aspect inside transformers, we use multiple heads for attention, not just single softmax, but multiple softmax to calculate different kind of attentions that we can think about. So this basically makes it multi-head attention instead of a single attention. And then you can like apply these multiple head attentions inside multiple layers to like refine context vector, which gives you a transformer. So basically a transformer block is like bunch of multiple multi-head attentions scale dot products, and then you can apply feed forward layer on top of it, and then some normalization that gives you a transform block. And then you can keep on doing it n times, and that gives you like a complete transformer architecture. So for example, like in the case of machine translation, which is what was the main task for attention, is all you need papers, the sequence to sequence learning. You can have like an input and then an output, then the values are accordingly calculated. So this is the transform architecture in nutshell. So you can see again, like this is like a zoomed in view of like what we just talked about. The multi-head attention is just bunch of scale dot products, and scale dot product is nothing just like a softmax multiplication with like a division with dimensions with the square root of the hidden dim. So once we know transformers, this is where it all starts. Once the transformer was introduced, like the field changed drastically. Like after like a year after the transformer was introduced to the field, they were prevalent everywhere in vision. Um, uh, Not after a year, but after 2 years, it was prevalent in vision. But it was already making rounds inside speech and even vision and language. And like NLP field was like very heavily influenced by the introduction of the transformers. So um, like we have already seen like specific examples which we will talk about, like of the success of like transform models in specific domains. For example, the first example is like BERT, which was like introduced a year after transform paper was introduced, which basically does a pre-training over text by masking some part of the text and trying to reconstruct it. And the BERT architecture itself is like bunch of transformer layers using self-attention to like figure out what exactly this mask would be. So in mask language modeling, which is the pre-training task that BERT uses, we would just mask one of the words of the input, and then just we will try to predict that masked word. So this is what the BERT used as a pre-training step. um, and this actually resulted in like a very strong unified trunk, which when fine-tuned on specific tasks in NLP would like outperform almost all of the prior work. Then after this, like in vision, we were introduced with the vision transformer, which is nothing but what it does is like takes like number of patches, square patches from the image, and then does a linear projection on top of them, and then passes them through a transformer encoder, which is again self-attention blocks, and then just like does some sort of like attention between those, and then passes the final vector through MLP head, and then through a classification layer. And basically what happens is uh, like if you see, this is also like a very simple architecture, like you're just dividing the whole model in a whole image inside bunch of patches, and then you're passing them through a transformer. They will do some sort of attention between each other, and then give you like a final vector which represents the crux of the image. And then you fine tune that representation on a specific task that you care about, for example ImageNet classification. And this also resulted in like very strong performance across the board, and VITs have sort of become like the standard in computer vision as well. And people have been like trying them on different kind of tasks like video classification, and then like also object detection, and like we have been seeing improvement all across the board. So this is where like transformers got introduced inside the vision side of the things. Then finally, in like multimodal, which is for our specific use case, image and language task, where like you need to like reason over both vision and language. For example, like in this particular case, if there is a question that needs to be answered based on the image, you have to like see the image and then answer the question. For example, in this particular case, if I asked you a question like, what did this person hit? So you have to see the image to understand that the person is hitting a ball, and then like correspondingly answer the question. So like visual BERT also was introduced after like the BERT paper, where they basically like use MLM tasks, but in the context of vision and language. So they take COCO dataset, which has like five captions per image, and they basically mask some part of that caption and try to predict that word that was masked. For example, in this case, like if I mask the ball, right? It's easy. It's through some bias. It's easy to figure out that the person was hitting the ball with a tennis racket. But let's say if I mask the tennis racket, right, and it's just like a person hits a ball with a dash, you definitely need to see the image to figure out what exactly was the context. So this task, even though it's very similar to MLM, the text side of MLM, it does require seeing the image to figure out like what exactly was the masked word. So basically, we call it multimodal MLM, where like the MLM is contextualized inside the image itself. Um, so like let's say like after witnessing like the success of transformers in specific domains, right? So we wanted to study a question that arises naturally, like could a transformer model when trained for like natural language inference on text input like BERT also perform object detection? Like let's say in this example, like there's a VIT and then there's a BERT that works on text side of the things. Can this VIT also work on text side of things, or is there like a joint transformer that can work across the domains? So, like overall, is it possible to build a single model that simultaneously handles tasks in variety of domains as a step towards general intelligence? Because that's what we will expect the final model that comes out of deep learning to be, right? Like, which can solve different kind of tasks together. And like, if yes, like how well that model can perform in practice. So, uh, yeah, turns out like this is actually possible, and we try to like learn different kind of tasks through a single transform model, which we call unified transformer in short unit. And like shown in this figure, we want to be able to simultaneously address vision only tasks such as detection and multimodal reasoning tasks such as VQA and language only tasks such as those in glue benchmark, all within a single shared model. So this figure is basically giving like a minor demo of what we want to do. So since we have like looked at the transformer architecture, um, unit is just unified transformer where we like have like a separate image encoder for like image side of the things, and then the separate text encoder for text side of the things. And these are two separate transformers which are like separately which are from one we are passing through the image and from one we are passing through a text. And then once we have like the output hidden state like we discussed previously from that multiple layers of the transformers, we concatenate these two outputs from the two encoders into a single output, and then we pass it through a decoder which is like a multimodal decoder. And basically it tries to like at each step based on the input that is given from the two encoders, it tries to like decode into like some output which is required by the corresponding task that we care about. So for the decoder, like the on the right side of the things, it learns like a more general set of query embedding vectors for multiple tasks. Let's say like if at a particular stage I care about VQA or SNLI or like blue task, we have like a separate query embedding vector which tells it like, okay, we want this task to be handled at a particular time step. So we at a moment we are jointly training across all of the tasks, but at a single moment there will be only one task in one batch, and there will be a query embedding vector that will tell you like which task we are currently talking about. So when we like pass the joint embedding from image and text inside the decoder, we also pass a query embedding vector like we talked before. Like there's a query value that we pass inside the transformer block at each step. So this query embedding tells transformer what we care about. Let's say we care about QNLI task from glue. So query embedding will be picked up for the QNLI and passed to the decoder. So that's how the model knows like this is a task we are talking about currently. So these query embeddings are also learned, and then after this, like after going through like some layers of the decoder, we have like a task specific head for each of the tasks. Let's say we are doing detection, we have a detection specific head. which also like outputs the bounding box. So this is like a very different kind of output compared to just outputting like whether like whether like two sentences entail each other or not, or whether like two questions are same or not. So that's like a binary or like a three-way classification compared to detection, which is more like a regression case where you are like actually outputting the bounding box, which are like coordinates of the bounding box. So that's the regression. So for like each task, we have like a separate head so that we can also take in consideration different kind of outputs that we want to give. So we call this model a unit, and it's inspired from a paper called Data. So that's like something that introduced, that paper is basically the first paper that introduced transformers inside vision, and specifically for the use case of object detection. So we hope that by training this model end to end on multiple tasks, we will be able to handle all of the tasks within this single model. So so if you particularly see this model, most of the architecture in this model is shared between the tasks. Only thing that is task specific is are the lightweight classifiers. Rest of the model, like encoder and decoders, are shared between the tasks. Excuse me. Uh, so let's talk about it whether it works or not. So that's the first question that arises in the mind. So like the answer is yes. So after some tweaking, so to be honest, like when we started working on this project, it wasn't like super straightforward to get this to work because we were almost sharing complete architecture, and the only thing that was different among the tasks was just those classifier heads that I just talked about. So there were like a lot of parameters that were shared. So the tasks compete with each other um, to like basically solve themselves. So there is like some competition between the parameter space that is shared between the models. So if you like there are like various ablations in the paper if you read it. Like if you like have like a separate decoder for each of the tasks and just share encoders, it becomes easier to train a joint model. But now you have like many number of decoders, which defeats the point of the paper. You're only sharing image and text encoders. So yeah, after some tweaking on learning rate and other hyperparameters, we were able to like converge on the 7 tasks across 8 datasets, ranging from object detection to language understanding in the glue benchmark and video question answering as well. So these tasks can all be addressed in a single encoder decoder transform model. For each task, we just either feed image or text or both of them into the encoder, and then feed its corresponding query embedding vector that we just talked about into a decoder and collect it output in the in the task specific head. So the interesting thing is like that we were able to get it to work, but it did require some of the fine tuning that I initially talked about as a key challenge when we are working across the multitask scenarios. So let's talk about whether it works on image alone. So that if the input is image only and the query embedding is per box vectors, so each task has its own query embedding vectors. For example, in like detection, we want to like get 100 object bounding box. So we pass in like a 100 dimensional query embedding vector, so the vector so that the model knows like it needs to output 100 different things, not just one. So in this case, we will just feed the image into the image encoder and just not pass anything inside the text encoder. So the final concatenation input will only contain the image encoded representation that will pass into the decoder. And then we like produce the box output. So the loss is backpropagated through the complete model in this case as well. And then does it work on text alone? Like for language only tasks, we only pass like text inside a text encoder and we don't pass any image. And then query embeddings are again per task vectors for classification output. So these are actually outputs from the model itself, the real model. So it does seem to work really well for most of the cases. And we will see the detailed results in some time. And similarly, like there are other tasks we can handle from like the text side as well. and these, even though these tasks compete, we lose some performance, but we are able to like converge all of them into a single model with some hyperparameter tuning. And similarly, does it work on image and text? For multimodal reasoning tasks such as VQA, yeah, we will feed both image and text, and a VQA query embedding vector so that it knows that it's working, that the model needs to answer VQA task as of now. So it does seem to work well for these kind of tasks as well. So, and then for like tasks such as SNLIV, so the task is basically like you are given a hypothesis, and there is an image. So you have to predict whether the image entails the hypothesis or not, and like similarly like whether it contradicts it or not. So like for in first example, there is a man in with sweatshirt in a wooden area, so the image does entail what is given. Similarly, in the second one, the dogs are not sleeping, so it's contradiction. So this also seems to work well for like unit model. So let's talk about numbers.
Sorry.
We
Hello. Excuse
Yeah,
me. We
yeah,
have some questions. So, like,
yeah,
can we go with them? Yeah.
yeah,
So,
sure.
one question is, could the visual BERT group have masked the image like in VIT without masking the text and have achieved any improvements?
When the visual word paper was introduced, we were not like using patches inside the image, so it was not straightforward to mask the image as such. So what happens is like before that time, we used to, in vision and language, we used to take faster and feature from the image, and then we will use those features as the image representation. So there wasn't like a one-to-one mapping between the features. So you can actually do like a mask region modeling where you will like mask the region, but you will mask the feature of that region, not the actual region inside the image, because there was no one-to-one correspondence between the features and back to the image. So there is, but it's not super easy to map through the anchors and all that stuff. So there were like losses such as masked region modeling, where they would mask the uh, region feature that would come out of faster RCN and try to regress through that feature, or like try to predict the object bounding box, like not the object bounding box, the object class for that feature if it's masked. But they were not super good in practicality, because what would happen is like faster RCN had like a very big dilation. So the rest of the features would cover up for the masked feature as well. So those were not very good in the practice. So we will talk about the masked image patches in sometimes as we move forward with the presentation. They do happen now, but they don't didn't used to happen before when Visual BERT was introduced. So it was not just possible at that point.
Yeah. And the next question is, usually in multilingual NLP, they achieve different embeddings by giving a language token in the beginning. Can you not do the same of different modalities?
Yes, so query embeddings are technically like something similar to what was just said, like the multilinguality, like you can give different kind of tokens. So it's just a different way of representation. So unit is more like an encoder decoder model. So we just pass those query embeddings directly inside the decoder, and we try to keep the text and the image encoder as task agnostic as possible. So this also like helps us like taking out the text and the vision encoder out of the model and just directly use them for like different purposes. So the query embeddings that we are talking about are very similar, but like a different kind of approach to achieve the same thing.
Yeah. And the last one is, did you use T5 like pre-training for unit for text?
No, so for this is like the first model that we first worked on. So like mostly like research is carried out in steps. So we before unit there was no model that even did this, like having these multiple models inside a single model, multiple modalities inside a single model, and then try to solve all these tasks using a single model. So we will talk about pre-training in some time, like because that's a natural next step that we will focus towards after this. But no, at this point, we were just concerned about like making the model work on multitask setting without any pre-training, because pre-training comes with its own set of complexities. So we didn't focus on it at this point.
Yeah,
Any other
that
questions?
sounds.
That's it.
No, no, no. We can proceed.
Yeah, thank you. Um, so yeah, so in this case, like we are comparing with like a well-established model in like each domain, and even though like unit is working well, compared to the prior work that is well established and is very domain specific, such as BERT, Visual BERT, and Data, there's still like some performance gap. So we actually anticipated this performance gap because specifically like in this case, we were like sharing the parameters. So the parameters was also like 8x less. So there was obviously like had to be like some drop from compared to like just using that model for that specific domain. So they were like drop all across the board, but like overall we were very happy with the performance of the unit, even though like we were using completely shared model across like end to end. So this like marked as one step towards like a general intelligence model which can work across modalities, and like one step towards like unified models across like tasks as well as modalities. So at by this point, like the field had started to look into multi-modality and like a possible alternative of not having like task specific models, and instead having like one model which can like also work on vision and text. And field has like came a long way since then, since unit has come, even though it has been only what like a year or so. It feels like a long time in deep learning, and there has been like a lot of progress. So let's talk about like how can we take this one step further. So I think we have somehow like discussed it in some minor detail according to the questions that were asked. So like in like any case, like pre-training or like the self-supervised pre-training has become like a norm inside deep learning. So you can't just leave the model without doing any sort of pre-training. So obvious next step to like improve unit is to like do some sort of pre-training, whether it's like through single domain, or whether you all use like multimodal domain, or whether you use a combination of all of them. So let's see like what exactly has happened in the field since Transformer was released. So first obvious thing that I think most of the people would know here is like BERT. So we already discussed BERT in some minor detail. So you take like a mask sentence where you mask some of the tokens, and then you also have like basically if you have a paragraph, you will have multiple sentences. You will mask multiple things in those sentences, and then you will try to predict those words again. So BERT also had like one extra loss which was called next sentence prediction loss, where it will just say whether the two sentences inside the paragraph were next to each other or not. So it can randomly sample the next sentence, and then then the NSP loss will become false. But with like future papers like Roberta, it came into a light that the NSP loss was not super helpful. With more data, you can basically cover up for the gap. So during fine tuning, they will like keep the complete trunk constant and just add a classifier on top of it. Sorry, they wouldn't keep the complete trunk constant because that wouldn't like give them the performance they're seeing. But they would fine tune through the whole trunk and just add like a classifier on top of it. And the trunk would start from the BERT pre-trained initialization, and it will give you like really great results on any of the tasks that you can think of. So like first task that they so the tasks that they reported in the paper were like glue, squad, and one more which I can't remember on top of my head. And they had like a really impressive performance across the board. And similarly in the vision, the thing that the question was asking. So we have like this sort of approach where we would like um, convert the image into patches and then use some sort of variational autoencoder, or like some sort of autoencoder to convert those patches into some sort of vocabulary, like some numbers, and then we will just mask those numbers and try to predict those back, and like predict those numbers, and then finally you can like regenerate the target using the predicted numbers. Let's say like there is you like convert the whole image into like a fixed vocabulary of 8K size. Then you can just train a autoencoder which encodes the image to those specific hidden states, and then try to regenerate based on those numbers. So you can like train this autoencoder independently, like something like a DALI paper is from OpenAI, and they do the same thing. So you can take this autoencoder and then just plug it inside the approach, and then basically use the masked auto basically mask it and then predict it again. So daddy in the original form, they didn't mask anything. They would just convert the image inside like the numbers, the hidden state or the latent representation, which were basically numbers, and they will try to like regenerate the image from those numbers. So in that sense, that model was very powerful. And then for like the masked autoencoders papers, and also the bead paper, which is BERT style pre-training for image transformers, that is from the Google, and masked autoencoder is from Meta AI. And both of these paper would like mask the image, some part of the patches, and then basically you will also get the encoded representation mask, and then you will try to like predict that encoded representation again, and then you will try to regenerate the target from that. So the beat paper, the original paper, they didn't generate the complete target back. They would just like predict the numbers and won't do anything further than that. And then, but the mass autoencoders went one step further and regenerated your target, which basically improved the model uh, better compared to the original beat paper. And then finally, in the multimodal side of the things, I think we have also discussed this in some detail. We have like two major kind of losses. One is like the mass multimodal modeling, which is similar to the MLM loss that is used in the BERT. You mask a word, or you can also mask like some part of the image, which in this case for the Wilbert paper, which is from where this image is. This mask is happening on the region features, not on the image itself, and you can mask and then try to predict them. So if you see the image more carefully, like on the image side, when it's masking the image, it's trying to predict the object that corresponds to that region that was masked. So it's not one to one what was done inside the MAE paper that we just saw, MAE and the BEAD paper. So this is mass multimodal learning. And then in the alignment prediction, you are given like a image and a sentence, and then you try to predict whether like these pairs match or not. So you can sample like random captions, and they will mismatch with the current image, and you can create like negative pairs for that. And actual change in the field came through the clip paper, uh, which was introduced by OpenAI, and where you would basically take they had like a 400 million image text pairs data set, which they didn't release. So the data set and the exact implementation details are not public. But basically what it would do is like take like n cross n image text pairs, and it will create an n cross n matrix, n cross n matrix, which will have its diagonal as one and rest of them as zero because they won't match. So your goal is to predict this matrix accurately. So basically, it's similar to the ITM loss, but it doesn't happen in a multimodal way. Like it's cross model rather than like being multimodal. So the text never sees the image, and the image never sees the text, or like cross, and there's no sort of any attention happening. So you just based on the text representation and the image representation, you are trying to figure out whether this image aligns with this text or not. So this is very different from ITM loss because it's happening in a cross model way rather than just happening on a multimodal way where they can attend on each other. So this paper actually was improved numbers quite a lot on the image side of the things, and showed that the multimodality can be like a useful alternative to not using any sort of pre-training for vision side of the things as well. So this helps to like ground image and text representation into a single space, because now image and text, like let's say there is an image and there is a caption, they need to have like a similar representation for the cosine product to be like really high. So this is where the whole idea comes from. But let's talk about like what were the motivation and challenges for us. Like we have seen all of the past works, and let's see what was the motivation for us in that particular case. So uh, even if you see now, the models either are working in one domain or the other domain. Let's say like BERT is working in the NLP domain, and then MA and Beta work in the CV domain. And similarly, VisualBERT, as we saw, works in vision and language domain, which is separate from vision and or language. But vision and language is like the task which require vision and language both. But VisualBERT will still not work well on the vision only tasks. So it will work well for like vision and language tasks, but it won't work well for vision tasks. So it will it can do multimodal tasks, but it can't do unimodal tasks. Similarly, clip, even though like the text representation and the image representation are grounded to each other, it works really well for CV tasks, but it doesn't really work well for like text tasks. So the catastrophic forgetting that we talked about, even though like they started from scratch, there was never a focus on like learning good representation for text. So they're still working in one domain or other domain. So we still not getting a unified model across these domains. Uh, so dataset used in these prior works are not like public or like or are not released. So this hinders like further research for like um, any kind of further research on clip style models, because we like collecting these data sets, large scale data sets, is very hard. And since like the prior work didn't make them public, it even made harder to like reproduce their research. So this is one other key challenge that we discussed in the start. Similarly, like prior work doesn't use any sort of like freely available unimodal data along with the multimodal data. So either they use unimodal data or either they use multimodal data, but they don't use combination of both of them. So like if you're using multimodal data and then you introduce unimodal data into a picture, it will obviously be better than just using multimodal data. So this is more like a hypothesis, but like we will show that in practice, it indeed is better based on the work that we recently did. So, um, so this is where we enter like our next work. So unit and flavor both are the works that were done with like a number of colleagues, multiple number of colleagues in Meta AI. So this was like more of like an extension to the unit with pre-training, but this ended up like a very different model than what we saw in the unit, and was like end-to-end single transformer without, not like really a single transformer, but without an encoder decoder style approach. So Flava is like foundational language and vision alignment model. So before we go further, are there any questions on the chat?
Currently, we do not have any question, but like if there's any, like I will let you know.
Yeah, sure. Thank you. So, so it's like one foundation model that can work across CV, NLP, and VNL, compared to unit which will also work on CV, NLP, and VNL. Like Flava works on like 35 different tasks from NLP, CV, and VNL domains. So the scope compared to unit, which only had like 9 data sets or 8 tasks, we increased the scope to 35 tasks, and it achieves very impressive performance on all 35 of them. So the major difference is like some minor architecture changes, and also like adding pre-training on top from both unimodal as well as multimodal domains. So yeah, it jointly pre-trains on unimodal text data, which is in our case we picked it up from Roberta, which is CC News plus book corpus, and then it also pre-trains on unimodal image data, which is ImageNet, and then it also pre-trains on public paired image text data, which is close to 70 million image text pairs, still much smaller compared to Clip, which is 400 million. But all of this data is public, and um, it basically allows leveraging data from all of the domain, and the code and data and models for everything will be public here compared to a prior work where we don't have access to the data. So everything was done on the public data. So the results are easily reproducible and everything. So how does Flava work? So this is the end goal, and what we want to fill in this white box here. Like you have like unpaired images, unpaired text, and like image text pairs. And then you are doing like visual recognition, also language understanding, and then multimodal reasoning, and then you're doing all these kind of tasks. There are like 35 different data sets that we are targeting here. So how do we fill in this box? So um, basically Flava pre-training loss is like combination of multiple losses from different domains. There's like a global contrastive loss, triple M loss, which we will discuss in some time. So let's see the Flava model in little bit detail here. So this is how the Flava model looks like. There is like an image encoder, then there is a text encoder, very similar to like unit model. But instead of having like a decoder, like with task specific queries, there is only one multimodal encoder that takes in all of the hidden states from image and text encoders and then just passes into a separate transformer, which we call multimodal encoder. So at the end, we have like multimodal hidden states, which we use for multimodal tasks. And specifically for like image tasks, we use image encoder, and then for the text tasks, we use text encoder. So we, as a sense of like why we did this, we were like trying to like separate the concerns that each encoder was caring about. So image encoder's responsibility is to like return an strong image representation that can be used in downstream tasks, but can also be used in image specific tasks. So to be very specific, like for vision tasks, we just take the CLS tokens representation from image encoder, and then we just add a classifier on top and then fine tune it for those specific case. So the numbers that we will be seeing are mostly linear probing numbers. Like we are not fine tuning the trunk for like the image side of the task. For the text side of the task and the multimodal side of the task, we are fine tuning the complete trunk end to end. So this is done to be more comparable to Clip, which doesn't fine tune end to end, just adds like a classifier on the top and just fine tunes that particular classifier and freezes the trunk. So in this particular image encoder's case, we are using a MIM loss, which we are generalizing the prior losses that we saw. Basically, it's the same thing that we saw in MAE and like beat loss. So MIE, we just call it masked image modeling because that's the more natural name of it. So we have like a Delhi encoder on top of image encode before the image encoder, which encodes these uh, image patches into like bunch of numbers, and then we take those hidden states and pass them through it, and then we try to predict those numbers, masked numbers from the image patches. So this is the only loss that we apply on image encoder, and there is no specific loss. So everything is more like a masked version of things. Then on the text side, we are only using MLM loss that BERT uses, also Roberta uses, and we take in text from, let's say, CC News, and then we mask some stuff in it, and then we just apply MLM loss on top of it. Similar to like the image side of the things, we basically use the text encoder as the only representation for NLP tasks. We take the CLS token from there and then like fine tune with the classifier on top for that specific task. So the job of the image and text encoder is to like give a strong image and text specific representation that we can use in downstream tasks, whether it's like multimodal retraining task or like even a multimodal task or like image specific or text specific unimodal task. So this is where like the multimodal encoder comes into the picture. It takes in the hidden state, complete all of the hidden state representations for each word in the text, and also each patch in the image directly inside as an input to the first layer of the multimodal encoder. So there is no word embedding or patch embedding in the multimodal encoder. It just takes in the hidden states directly. So then on the top, we have like a 6-layer multimodal encoder, where we like at the end, we do similar losses like ITM loss, which we talked about, image text matching alignment loss, where you like figure out whether the particular image and text match or not, or whether they mismatch. And then we also create a new lower loss, which we call masked multimodal modeling, where like is similar to MIM, but in the case of the paired data, we have both image and text. So we mask both of them on the both sides, and then we try to predict them through the multimodal encoder rather than image encoder and text encoder. So as I discussed before, like for the captioning data, it's important to have the image with it if you mask the caption to predict the missing word in the caption, because otherwise it won't have context to complete that particular text. So we are talking about two different things. So MIM loss is only applied when you have like unimodal data, and MLM loss on the text side is only applied when you are figuring out the unimodal text data. When you have multimodal data, which is paired data, you basically apply masked multimodal modeling loss, which is calculated through multimodal encoder, not like text and image encoder. Because to complete those, both of them, you need caption of the image for like both sides of the things. So the mass multimodal loss works really well in practice. So we apply it on the top of the mass multimodal, the multimodal encoder. And then finally, the multimodal task heads are applied on the top of the CLS token that we add to the multimodal encoder, and then we just fine tune it end to end. Then further, there is one more loss that we add by being expired for the clip is the cross contrastive loss, global contrastive loss on the image encoder and the text encoder representations, so that they are also grounded in each other and we like get the benefits of the paired data inside the unimodal representations as well. Because if you see, if you don't apply this global contrastive loss, what you will get is just MIM loss and the MLM loss on the text and the image encoder, and some back propagation through triple M and ITM loss from the multimodal encoder. So GC loss helps basically boost the text and image representation by learning through the paired data as well instead of just being unimodal data. So the model itself is quite complex and it has like 5-6 losses in the picture. And again, like with unit, we had to like do some sort of hyperparameter fine tuning or like um, some sort of control mechanism to like have these all of these losses work together. But in the end, like we were able to make them work with minor tweaks, and like we didn't do anything special in this case. They would just work out of the box really well with like minor adjustment to the sampling ratios of the each data set. So this turned out like working quite well from the out of the box itself. Then we talked about the pair data. So minor description on it, like we just combined all of the public various multimodal sources that were available at that point. I think at that point it contained like 8 different data sets, including YFCC filtered subset that Clip also uses in releasing its YFCC subset version. But we don't have the exact mechanism of how they filter out YFCC. So we had our own mechanism, which gave us like 15 million data image pairs from there. So this turns out like a 70 million image text pair data set that we use for like the multimodal side of the things. Then we also did like some further improvements here, like we didn't wanted to like lose the prior knowledge that we already had from like only single task specific training from unimodal encoders, such as like Roberta trained on MLM alone without any sort of like multimodal encoders or like any sort of multimodal loss. So we would start from them instead of like starting from scratch, because it will give the text encoder a good starting point for initialization. Similarly, we will use the Dino VIT for image, like image side of the things. We will initialize the image encoder from the Dino checkpoint. Then we also use random augmentation in the images, as we saw that it didn't really matter if you like crop the image a little bit for contrastive loss. That gave us some boost. And then we also tried different sampling ratio to get a stable multitask strategy between data from 3 different domains that we just talked about. So we would like sample, move around between the 3 different data sets. So usually because the unimodal encoders were initialized from pre-trained weights, we would sample the unimodal data lesser compared to the paired data, but we will still sample it so that we don't face catastrophic forgetting, which will make them to forget about text tasks at all. So that's why you need to sample unimodal data, because if you don't sample it with time, the model will eventually lose all of the information that it learned about like just text. So we will usually sample it after some point of the time so that we can keep on remembering what we knew about the text. So some numbers on it. So you can scan the QR code on the top if you want to see the complete table on 35 downstream tasks. It's too big to fit into this slide. So these are just some numbers from it. So the numbers on Flava improved quite a lot compared to like unit model for like vision and language tasks. And like ImageNet accuracy, even though it's lower than Click, which was trained on like much more data, it's still impressive. There's only like a 4% gap. And we hope that we are hoping that as we match the gap in the paired data, we will be able to match it. But compared to Clip on like text side, we are doing much better, which gives us like a higher macro average across tasks, including like the vision and language tasks. There are like 9 or 10 of them in the paper, and we beat Clip on almost all of them. And compared to visual BERT, which is like a multimodal model specific to vision language tasks, we still beat it. And there are other baselines also inside the paper compared to them, which we are doing really well. So there's still some gap compared to BERT, but we are like quite close to BERT now compared to like how much gap there was with the unit paper. So we are doing really well, and in the future we are like focusing, trying to like improve the language side of the things even further. So you can also see the paper for more details. I think the final question is like, given this big model, like how much compute it would have taken to like train this one. So as of now, yeah, it's very compute heavy. Like it was trained on 128 GPUs for a week for 400K updates with a batch size of 8K. So it does take a long time, but we did do efficient pre-training using fully sharded data parallel and like also checkpoint activation and FP60 training. So model is very small though, like not very heavy compared to the prior models that we also like the new models that we are seeing all across the board. But even with this small number of parameters, it still have very impressive performance compared to the recent models that we are seeing in the multimodal field, which are very heavy and use like billions of data, paired data. Uh, so yeah, it's still working quite well. So let's just revisit the key challenges that we discussed initially so that we see like what are the takeaways from this task. So as we initially said, like the architectures are two domain specific. I think that problem is kind of solved through transformers, unless like a new building block comes into the picture which can be transformed in all of these tasks. So for like uh, overcoming this problem, I think transformers is a good solution. And then for cross-model pair data is not abundantly available. We will be releasing PMD through Hugging Face datasets. So that's like a good source of data than not having any data as of now. And I think with these kind of papers like flavor that we are releasing, I hope that the community will be adding more and more paired data to the picture as well. So jointly learning across domains is hard. I think there are like great takeaways from the flavor paper on how to like jointly learn across domains and also how to do multitasking. So you can use flavor pre-training schemes and the flavor papers takeaways to like jointly learn across domains. Finally, requires heavy compute. Yeah, so you can use advancements in infra like FSDP, checkpointing, and FP16, but like this is always a work in progress. Like, how can we achieve similar scales by using a smaller batch size rather than using such a big batch size? But as the field is moving towards bigger and bigger models, there is still work that is happening on like making these models again smaller and achieving similar gains through distillation and other things. So yeah, this is still a work in progress, and the field is making progress on it. So yeah, future. So I think for the viewers of this task, I think there are like interesting challenges that are still open. For example, like I don't think we have like fully used PMD to its full potential. I think with augmentations and other kind of data transformers or other kind of like data generation strategies which can be trained on PMD, we can still further improve flavor model. And then there is also like a gap in language understanding compared to BERT. I think the true revolution will come when we will beat BERT also on the unified encoder and model. If we beat BERT, then we will be beating the prior work on all domains with a single model. So those are some of the things, and then also like scaling this model further. So Flavor model as of now only uses 12 layers on both sides for vision and text and a 6-layer multimodal encoder. So there is obviously some scope to like scale this further. So our main goal was for this paper was to like see if this can work or not the scaling expert. So there is obviously some chance to like improve the numbers further by scaling the model. And yeah, thank you. So the summary is like unit, we introduced unit, which extends like encoder decoder with generic query embeddings for like other kind of tasks. And is a single transformer converging well on multiple tasks across the domains. Is the unit's code is already open source in the MMF framework. And then Flavor is a single model with impressive performance and does pre-training on does pre-training and then has impressive performance on 35 downstream tasks. And then it also pre-trains using data from all three domains. So it's also pre-trained on publicly available data, which will be the PMD dataset, which will be released through Hugging Face dataset soon. And the code for Flava is not open source as of now, but we are working on releasing it through Torch Multimodal, which is a new library that will be releasing through PyTorch ecosystem soon. And it will also be available in Hugging Face transformers. So let's open up for any questions that are there regarding the talk.
Yeah, we have a question. Just let me- yeah. So the question is, if you use Robota to initialize your text encoder, how is the model performing worse than better? Since the language encoder is separate.
Um, I see. So basically, like if we had used BERT instead of Roberta, like how would it have performed? Is that the question, if I understood it correctly?
Hmm, just let me confirm. So the question, I will repeat the question. If you use Robota to initialize your text encoder, how is the model performing worse than BERT since the language encoder is separate?
Oh,
Like, was there
I
any
see.
analysis done on this aspect?
Oh yeah, so I think there is like ablations inside the paper specifically for the losses that we just discussed, and the main reason why it's performing worse than BERT is the reason that we were discussing in the start, that is catastrophic forgetting. So as you like try to do multiple tasks with a single model, there is obviously like something that you will lose in the same set of parameters. So as you're trying to optimize for more, you will lose some task domain specific knowledge that we call catastrophic forgetting. So that's still one of the open problems that is like one of the different fields like continual learning on how don't we forget like what we already learned. So like if we talk about the real AGI, like the artificial general intelligence, what would happen is that it won't forget what it already learned. But as of now, as you like try to extend beyond just one single domain, it will definitely like forget some of the things that it learned in that specific domain. So one of the core aims of Flava was to like avoid catastrophic forgetting as much as possible by resampling the MLM or Roberta data during the training. But as much as we try to prevent it, it still happens with time. So yeah, we are working on like improving the tech side of the things, and that's one of the open questions that we have as of now.
Thanks, Amanpreet. And if someone has a question, they can put in the comment section.
Yeah, thank you. Anyway, like if they can still reach out to me by my email, my first name at nyu.edu. So you can just reach out to me if you have any other further questions or you need a flavor. Or I don't know, like if YouTube comments are still active after the live chat, they probably are. So you can also comment there and I can reply to you.
Okay, so we do not have any more questions, so we can end this live stream. Thanks, Amanpreet, for this very exciting lecture, and thanks to everyone for joining. And let see you all tomorrow on tomorrow's lecture.
Thank you. Thank you for hosting me. And thank you everyone for listening.